Welcome to the deep dive. Ever used GPS to find your way around? Well, what if that map covered the entire universe?
Hmm.
Today, we're diving into how astronomers map the cosmos using what are called celestial reference frames.
Yeah,
You can sort of think of them like the ultimate longitude and latitude for space.
that's a good way to put it, yeah.
Our mission, to understand how these cosmic maps are created and, crucially, kept accurate, especially thanks to, well, groundbreaking space telescopes. We'll be using a fascinating document that charts this very evolution.
Exactly. I mean, imagine trying to tell someone exactly where a specific star is. Without a shared system, it would just be chaos, wouldn't it?
Total chaos.
A celestial reference frame gives us that common language, a way for all astronomers everywhere to agree on the locations of objects in space. If you've ever looked up at the stars and wondered how, ancient navigators use them, you've already got a sense of why this is so important.
So, our deep dive today is all about unpacking how astronomers establish the starting point, the origin for these cosmic maps, and maybe even more crucially, how they maintain their precision over time.
Uh,
And we're really focusing on the revolutionary impact of space-based observatories like Hipparcos and Gaia.
right. Maybe we should start by looking back a bit at the challenges astronomers face trying to map the heavens from, well, down here on Earth, before we had the advantage of space-based telescopes.
Yeah, good idea. Because peering through our atmosphere turned out to be, well, a major hurdle, didn't it?
Oh, definitely. Ground-based measurements could mainly only tell you the positions of stars relative to their immediate neighbors. It was all very localized.
It's like trying to create a map of the whole world by only looking out of your own window, right? You might
Yeah.
get your street perfect, but the bigger picture would be kind of blurry and distorted.
Exactly. And our document notes that even the best star positions, compiled before Hipparcos came along, had these systematic errors of about zero point 0.2 to zero point 0.3 arcseconds.
Which might not sound like much, but across the vastness of space, that's a pretty significant wobble.
It really is. And what's fascinating here is how astronomers even decided on the initial 0 point for this celestial map in the first place. It's not like there's a cosmic equivalent of, say, Greenwich or the North Pole just conveniently hanging out there.
Okay, let's unpack the basics then. Just like we use longitude and latitude on Earth, astronomers use right ascension and declination.
Right.
Declination is fairly straightforward. It's basically the angle north or south of the Earth's celestial equator, running from 0 up to plus 90 degrees or down to 90 degrees, just like latitude.
Uh-huh.
Simple enough. But the starting point for right ascension, which is the equivalent of longitude, that has more historical and maybe in some ways almost arbitrary origin. It's called the first point of Aries, also known as the vernal equinox.
And as our document explains, this first point of Aries was defined way, way back by Hipparchus around 130 BCE. Quite amazing, really.
Wow.
It's one of the two spots where the celestial equator, that imaginary circle in the sky directly above Earth's equator, intersects with the ecliptic, which is, the plane of Earth's orbit around the sun.
So it's a clever way to anchor the system back then.
It was, but it was fundamentally tied to Earth's movements. And
Yep.
that's the catch.
And that's where things get a bit, well, shaky, isn't it? Because our Earth isn't just spinning smoothly like a perfect top. Its axis of rotation itself is slowly wobbling.
Like a slightly off-center spinning top, yeah. It's called precession.
Precession, and it takes a staggering 26,000 years for one complete wobble.
It's incredibly slow, but
Mhm.
measurable. And the document points out that this causes the apparent coordinates of celestial objects to constantly change about 1 degree in right ascension every 70 years or so.
So the very map itself was slowly but surely drifting, just because our viewing platform, Earth, is wobbling.
Precisely. And if we connect this to the bigger picture, you can see why this movement, precession, along with other more subtle motions like nutation, which is like a small nodding in the Earth's rotation.
Right, like little ripples on top of the big wobble.
Kinda, yeah. And also polar motion, the actual poles shifting slightly. All this made precise celestial mapping from Earth incredibly difficult.
So astronomers had to keep updating their reference systems, didn't they? Specifying them for different time periods or epochs like B 1875, B 1900, B 1950, and the more recent J 2000.
Exactly. So if you were using a star chart from, say, 1900, the coordinates wouldn't perfectly match a modern one because the entire framework, the grid itself, had subtly shifted.
And even within these systems, the stars themselves are moving due to what's called proper motion.
Right, proper motion. That's the star's own individual movements across the sky relative to us.
Right.
They aren't fixed points of light. They're drifting, albeit very, very slowly from our perspective.
So it's like trying to navigate with a map drawn on a piece of paper that's not only shaking, but also has all the landmarks slowly inching around.
That's a great analogy. And as our ability to measure star positions became more refined, more accurate, these complex motions of the Earth became an even bigger obstacle to overcome. You really had to model them precisely.
It wasn't just the gravitational pull of the sun and moon causing precession and nutation, right? The document mentions other factors, too.
Yeah, it gets even more complicated.
Yeah.
There are a whole host of internal and external factors affecting Earth's spin, the movement of oceans, tectonic plates shifting, even things like climate and seasonal changes.
Wow. Who knew our planet was such a restless platform for stargazing?
Exactly. So facing these increasing difficulties in sort of untangling Earth's complex movements from the actual positions of stars, astronomers began looking for a more stable foundation for their cosmic map.
Made sense.
And this is where the idea of a dynamical reference system emerged. The idea was to link it to the motion of objects within our solar system planets, asteroids, hoping that would be less affected by Earth's specific antics.
Okay, and then in the 1990s, there was a real leap forward, wasn't there, with radio astronomy?
Yes, very long baseline interferometry, or VLBI. This technique allowed for incredibly precise radio measurements of a few dozen radio stars, but crucially, also these extremely distant objects called quasars.
Quasars, those super bright centers of distant galaxies.
That's them. And our document highlights that these radio VLBI measurements achieved significantly greater accuracy than the traditional optical methods from the ground could at the time.
So what was the impact of that?
Well, it was pretty transformative. The International Astronomical Union recognized this significant advancement and essentially shifted the official celestial reference system to one defined at radio frequencies.
Okay.
And this new system, the ICRF, or International Celestial Reference Frame, was anchored to those incredibly distant quasars. The beauty of quasars is that they are so far away.
Billions of light years, right?
Billions, yes. They appear virtually stationary on the sky over human timescales. They provide a much, much better approximation of what physicists call an inertial reference frame.
An inertial frame. So like a viewpoint that isn't accelerating or rotating, offering the most stable perspective possible.
Exactly. It's fundamentally decoupled from the wobble and spin of the Earth.
Okay, so we've moved from Earth-based wobbly coordinates to a more stable radio-based system anchored to the distant universe. But the next step was truly revolutionary, getting our telescopes above the Earth's atmosphere.
Ah, yes. Space astrometry.
Yeah.
Missions like Hipparcos and Gaia. The document really emphasizes this. They achieved vastly improved accuracy simply by observing from space.
No more atmospheric blurring or bending of light?
Right. That alone was huge. But it wasn't just about having a clearer view. As the text points out, by being in space, these telescopes were immediately free from dealing with all those hugely complex effects of Earth's spin-axis motion, the precession, nutation, polar motion.
Ah, so they bypassed that whole problem. That's a massive simplification right there.
Absolutely massive.
But it gets even more ingenious. Both Hipparcos and Gaia employed this brilliant technique. They had two separate fields of view on the sky, angled apart by a very specific amount.
And they superimposed these views onto a single detector. This idea, pioneered by Lecruit and Lindegren, is really key, isn't it?
It really is. Hipparcos used an angle of 59 degrees between its fields of view, while Gaia used 106 degrees. And the document mentions something important. Using an angle that isn't a simple fraction of 360 degrees, like not 90 or 180, that's crucial for creating a very rigid reference frame across the entire sky.
Okay, why is that specific angle thing so important? Why not just 90 degrees?
Well, the non-repeating nature of that angle as a satellite spins and scans the sky means that the measurements link together stars across wide angular separations in a very complex overlapping way. It prevents systematic errors from building up in particular regions of the sky. You get a much more uniform and interconnected set of measurements covering the whole celestial sphere.
Ah, okay. It knits the whole map together more tightly.
Precisely. And the result, as the text highlights, is profound. It enables what's called absolute parallax measurements. Absolute parallax, that sounds really important. What does that mean for our cosmic map? How is it different from just parallax?
It means that a star's parallax, that tiny apparent shift in its position we see as the Earth orbits the sun, which is fundamental for measuring its distance.
Right, the triangulation thing.
Exactly. With this technique, that parallax is no longer determined just relative to other nearby stars in the field of view. Instead, every single star measured by Hipparcos or Gaia has its parallax determined on the same absolute scale with the same 0 point.
Got it. So it's a much more robust and accurate way of determining distances across the whole cosmos, not just locally.
Much more robust, yes.
However, even with these incredibly sophisticated space telescopes, achieving perfect accuracy isn't quite straightforward.
Yeah.
The document points out two remaining challenges. One is precisely establishing the 0 point of this absolute parallax scale. What's the other hurdle?
The second one is a bit more subtle, a bit more technical. Turns out that very tiny systematic changes in the angle between those two viewing directions on the satellite itself,
Uh-huh.
especially if these tiny changes happen in sync with the satellite's rotation, maybe repeating every certain number of spins, this can create an effect that looks almost identical to a common error in the parallax 0 point for all the stars. It's very difficult to distinguish the two effects.
Ah, so it's like a minuscule instrumental wobble that could be mistaken for a fundamental property of the stars themselves,
Right.
or rather our measurement of their distances.
Exactly. And the document mentions that the way the sun's light hits and warms the spinning satellite could potentially cause tiny thermal flexures that lead to this effect.
Right, so it sounds like the engineers who designed Hipparcos and Gaia had a real challenge on their hands to build the satellite stable enough to minimize this dependency.
Oh, absolutely. Huge efforts went into thermal control and structural stability.
Yeah.
And that brings us to the crucial next step. Connecting these new, highly precise space-based reference frames to the established extragalactic frame, the one defined by those distant quasars using radio VLBI.
Right, because you want to make sure your new, highly precise optical map is properly oriented and not sort of drifting or rotating relative to the most stable thing we know, the distant universe.
Precisely. This was a major objective for the Hipparcos mission back in the day.
Okay, so the plan was to include certain stars in Hipparcos's observation program that could later be used as tie points, right? To link its rigid frame to this inertial extragalactic framework defined by the radio quasars.
That was the plan. And this would allow astronomers to estimate and correct for any tiny residual error in that parallax 0 point, and also to determine the overall orientation and, importantly, check if the Hipparcos coordinate frame itself had any slow residual rotation.
But there was a limitation with Hipparcos, wasn't there? Something about how faint it could see.
Yes, a significant one.
Yeah.
Because Hipparcos had a limit on how faint the objects it could observe were around magnitude 12, which is relatively bright in astronomical terms. It meant that only one faint quasar, the famous 3C273, was actually bright enough to be included directly in its observations. And even that single observation didn't provide a very strong link on its own.
Only one quasar. So how did they manage to bridge that gap then? How did they connect Hipparcos's optical frame to the extragalactic radio frame? The document mentions a substantial effort involving several research groups and less direct techniques. What did that actually involve?
It was a real piece of astronautical detective work. Quite ingenious, really. Researchers used a whole variety of methods. They combined radio wave observations of certain stars, radio stars, with the optical observations from Hipparcos for the same stars.
Okay, finding objects visible in both radio and optical.
Exactly. They also observed quasars relative to nearby Hipparcos stars using other instruments like ground-based telescopes with CCD cameras, and even the Hubble Space Telescope.
Ah, using Hipparcos stars as stepping stones.
Yes. And they used old photographic surveys to measure the apparent motions, the proper motions, of stars compared to very distant background galaxies, assuming the galaxies were fixed points. Plus, they even compared measurements of Earth's orientation, how the Earth is spinning and wobbling, obtained from VLBI radio observations, with those derived from Hipparcos data.
Wow, that's a lot of different approaches all woven together.
It was a huge collaborative effort.
And after all that meticulous work, what was the outcome? How well did they succeed in aligning the Hipparcos catalog with the extragalactic radio frame?
Well, the document states that the coordinate axes of the final Hipparcos catalog were believed to be aligned with the extragalactic radio frame to within about plus or minus 0.6 milliarc seconds at the middle of its data-taking period around 1991.
0.6 milliarc seconds. That sounds incredibly tiny.
It is incredibly tiny. And just as importantly, the frame was estimated to be non-rotating with respect to those distant extragalactic objects to within about plus or minus 0.25 milliarc seconds per year.
Wow.
Which is a remarkable achievement, especially considering the very indirect approach they had to take because of that magnitude limit.
Amazing. So Hipparcos gave us a much, much more precise map. And they managed, through all this effort, to tie it pretty securely to the most stable landmarks in the universe. But then came Gaia. totally different story, yeah.
Absolutely. Gaia was a game changer in this respect. The document highlights one crucial difference. Gaia could see much, much fainter objects than Hipparcos, reaching down to magnitudes 20 or even 21.
Okay, and what did that enable?
That huge increase in sensitivity opened up the possibility of directly observing vast numbers of quasars, not just one, but hundreds of thousands of them, spread all across the entire sky.
Hundreds of thousands. The document mentions an estimated 500,000 quasars with an average density of about 25 per square degree. That's just an incredible census of the distant universe.
That really is.
So how did this direct observation of so many quasars change everything for building the reference frame?
Well, it allowed for a much more direct, much more robust way to link the optical reference frame, the one Gaia was creating, in visible light, directly to the extragalactic frame defined by those same quasars.
So no need for all those indirect stepping stones and complex comparisons used for Hipparcos.
Largely, no. Gaia could essentially build its reference frame directly upon these incredibly distant, seemingly fixed points scattered all over the universe. So it's a much cleaner, more fundamental approach.
And the document mentions that the teams planning Gaia really thought hard about potential challenges, even with this approach. Things like checking if quasars are uniformly distributed, or if there were any color-related biases, or tiny instrumental changes.
Yes, exactly. During Gaia's feasibility studies, they looked very closely at issues like sky uniformity, potential color dependencies in the measurements, and whether tiny structural changes within the Gaia instrument itself over the mission lifetime could introduce subtle distortions. They really tried to anticipate the problems.
Okay, so let's jump to the results. The document mentions Gaia Data Release 2, which came out in 2018. What did that tell us about our cosmic map? Was the potential realized?
Oh, yes. Even with less than 40% of the data expected from its full nominal mission, Gaia DR2 provided the precise positions of over 500,000 quasars, 556,869 to be exact.
Wow.
And these positions were used to define a kinematically non-rotating reference frame in the optical part of the spectrum that met all the strict prescriptions of the International Celestial Reference System. And crucially, as we said, it was built directly on those extragalactic sources.
That's incredible. So for the first time, we had a highly accurate optical reference frame anchored directly to the most distant objects we can observe across the whole sky. How did its accuracy compare to the existing radio frame, the ICRF?
Well, the document states that its accuracy actually matched that of the current radio frame, the ICRF-3 at the time. But, and this is key, it did so with a much, much higher density of reference points those quasars spread across the sky.
More points to pin the map down.
Exactly. The typical uncertainty in the positions of these quasars in Gaia DR2 was remarkably small, just 0.12 milliarc seconds for the brighter ones, and about 0.5 milliarc seconds for the fainter ones at magnitude 20.
Still incredibly precise.
Extremely. And even the larger scale systematic errors, potential distortions across the whole sky were impressively low, down in the range of 20 to 30 microarc seconds.
Arc seconds, that's tiny.
Vanishingly small. And when they compare the optical positions from Gaia with the radio positions from the ICRF for about 2,800 sources that were visible in both, they found very good overall agreement.
So, as the document emphasizes, already back in 2018, we had achieved the first realization of a truly global, non-rotating optical reference frame built directly on extragalactic sources. That really does feel like a monumental achievement in our ability to map the cosmos.
It absolutely was a huge milestone for astrometry and for astronomy in general.
And this level of precision, it isn't just about knowing exactly where things are, is it? The document briefly touches upon potential cosmological implications.
That's right. Having such an incredibly accurate and stable reference frame opens up possibilities for measuring effects that were previously thought to be far too small to detect. For instance, the document mentions the possibility, explored in other research, of detecting the extremely subtle tumbling motion of a non-spherical or triaxial halo of dark matter surrounding a galaxy like Andromeda.
Wow, that's mind-blowing. So this incredibly precise cosmic coordinate system could potentially help us investigate the very nature of dark matter and the large-scale structure of the universe by measuring these tiny, tiny effects.
Exactly. It highlights how seemingly technical advancements in measurement techniques and reference frames can actually open up entirely new avenues for probing fundamental scientific questions about the cosmos.
So to kind of bring it all together, we've really journeyed from the real limitations of mapping the sky from the ground, constantly wrestling with Earth's own movements, to the revolutionary precision offered by getting into space with missions like Hipparcos and especially Gaia.
Yeah, the key has been the ability to observe from above our distorting atmosphere, and crucially with Gaia, to directly anchor our cosmic map to vast numbers of incredibly distant quasars,
We've transitioned from a celestial coordinate system that was, inevitably somewhat tied to our own moving, wobbling planet.
to one that is firmly anchored in the distant, seemingly stable extragalactic universe. It provides a much more reliable and fundamentally accurate foundation for pretty much all of astronomy.
It really makes you think about the sheer scale of this endeavor. We're essentially creating this incredibly detailed and accurate map of the entire observable universe. What future astronomical breakthroughs might this enable? How might it even refine our understanding of fundamental physics and cosmology in ways we can't even imagine yet?
It's a profound achievement, no doubt.
It's something really amazing to consider.
Indeed. It just invites us to ponder, doesn't it? How deeply our understanding of the universe is intertwined with our ability to map it with ever-increasing accuracy.